Hello, this is Gustav Nelson doing my 3D model volume project presentation for Math 152, and the object that I'm modeling is an hourglass container, specifically the container itself, which is the glass, and not the volume which the sand would contain. In order to model this, I'm going to need four functions: absolute value of sine x plus 0.05, absolute value sine x, and then two constant functions, 0.1 and 0.05. The two sine functions create the majority of the wall of the hourglass, and I have one of them translated 0.05 up to create that wall thickness everywhere, and they are absolute values so that I can more easily rotate them around the x-axis. Now, if I just had these sine values, then they would go down, sine x would go down to 0, where sine x plus 0.05 would go to 0.05, and when I rotated it, I would end up with a solid portion here, and no sand could be able to pass through it. So I created this 0.1 and 0.05 thickness layer, which will act as the thickness of the wall from B to C, and those B to C will be from when sine x goes below 0.05 and when it rises up to 0.05 again. I had to choose some cutoff regions for the regions of integration, and that's because an hourglass obviously has flat tops. So I chose, this whole thing goes from 0 to 2 pi, so I chose 0.4 pi and 1.6 pi. And this is that same graph resized to show those limits. And I also put these lines here, which will be the limits from A to B, B to C, and then from C to D. In order to find the volume, I'm going to be using the washer method. So here I have pi multiplied by r out squared minus r in squared multiplied by the thickness. And because we're doing the Riemann sum, I'm going to be taking 30 slices. So I have 1.6 pi minus 0.4 pi divided by 30 to end up with a delta x of 0.125664. So I need two different volume equations, one for the sine functions and one for the constant function. So this one shows that for the sine, which can be reduced down to pi times 0.1 times absolute value sine x plus 0.0025 times delta x. And for the constant function, it reduces down to pi times 0.0075 delta x. So I know the regions of integration are from A to B, B to C, and C to D. And I know A is 0.4 pi, and I know D is 1.6 pi. But I don't know the specific values of B and C. But I do know that B is the point where sine x is 0.05, and also is the point where C is also where sine x is 0.05. However, if you put that into your calculator, you're going to get a value that's much smaller. In fact, you'll get this value over here. And that's because your calculator gets you the first value that fits that parameter, which is not a big deal because we know that this value is 0 here, sine here is also 0, and that value is the absolute value away from sine equals 0. So I can simply take pi minus and plus the arc sine of 0.05 to get those values that are actually around the pi x. So you do that, and I get 3.09157 and 3.19161. So now I have all the points I need to do my Riemann sums. And now I need to calculate the midpoint values. So because I'm taking from I equals 1 to I equals 30, I'm going to start at 0.4 pi plus I delta x, which is then added to 0.4 pi plus I minus 1 times delta x. So that gives you the first x value. That gives you the x value before it. And divide all that by 2 will give you the average of those, which can be reduced down to 0.4 pi plus delta xi minus delta x over 2 from I equals 1 to 30. So here are those three Riemann sums. 1 to 14 is A to B, which is 0.1 times the absolute value of sine times that average value equation plus 0.0025. And all of this gives you the radius squared. That times pi gives you the area, and all that times delta x gives you the volume. And that's the same thing from C to D, only now we have I equals 17 to I equals 30. And from B to C, it's simply a constant function, 0.0075. And when you add all those together, you get 0.85162. So this is our calculated volume using the Riemann sum. This is the table of slices from I equals 1 to 30. This shows you the average x value that was used to calculate that slice, and this shows you the actual volume of that slice. And you know we've done this right because 15 and 16 are the same because these are the constant functions. And then from 1 to 14 mirrors 30 to 17. So here at 1 we have 0.0392, 30, 0.0392. At 14 we have 0.00838. At 17 we have 0.00838. And then to calculate the theoretical volume, we integrate. You can't actually find the integral because you have the absolute value. So instead you have to find the definite integral using your calculator of pi times 0.1 times absolute value sine x plus 0.0025 from x is 0.4 pi to 3.09157. You do the same thing from C to D, only from 3.19161 to 1.6 pi. And then you can integrate pi times 0.007 pi 5 from B to C. And when you do that, we get this value, 0.852874, which is very similar to that 0.85162 value. But we can actually calculate this indefinite integral and therefore do a proper integration if instead of having an absolute value of sine, we have sine x plus 0.05, sine x, 0.1, 0.05, and then negative sine x plus 0.05 and negative sine x. And these four basically create the absolute value function because once we get past pi, and we're now from pi to 2 pi, the sine function becomes negative. So taking the negative of the sine makes it a regular sine function. We can calculate those integrations. So you end up with, for the sine plus 0.05 squared minus sine squared, you get negative 0.1 cosine x plus 0.0025x. For the negative sine plus 0.05 squared minus negative sine squared, you get 0.1 cosine times x, 0.1 cosine x plus 0.0025x. And for that constant integration, you get 0.0075x. And each of those is multiplied by pi. When you calculate all of that, you get the exact same answer, 0.852874. So we know this is right. This appendix just shows all the stuff I used to calculate those graphs and everything. And here we have a 3D model that I made on Fusion 360, which shows the entirety of the hourglass shape. Notice that that open part right here would not exist if we didn't have those constant functions. Here I'll show you what it looks like with a cross-section area. And if you actually use the software to calculate the volume, we get 0.936 cubic units, which is significantly different from the 0.852 that I got on my math software. But that makes sense because Fusion 360 is much less precise. It only goes to the thousands place, whereas my math software can go to like the 10th or 11th digit. This is my 3D model that I made of the cross section. It was made using a 3D printed parts. You see that it is hollow on the inside. The golden ones are the ones using sine function, and the blue one is using that constant function.